So I gave this help to the other class, so I wanted to share it with you guys as well. We went over question 14.34 in class on Thursday. We're basically given a reaction, and we run the reaction 3 different times where we vary the concentrations and determine, we observe the change in rates, and that allows us to determine the rate law for that reaction. And I also gave them this shortcut to basically figure out what order the reaction is for each reagent in the reaction, and that equation is concentration final divided by concentration initial, all raised to an exponent that we're trying to find. That's the order with respect to the chemical we're looking at, and that equals rate final divided by rate initial. And so to start, I looked at over here entry 1 and 2, right? Concentration of hydroxides remaining constant, so that's helpful for us because we can look at this change in rate and directly relate to this change in concentration. So it's easier, instead of concentration final, just doing the highest concentration, which should lead to the fastest rate. So to have the largest numbers on top, so 0.06 molar divided by 0.02 molar equals 0.0248 molar per second divided by 0.00276 molar per second. Divide those through, we get 3 raised to the x equals 9. Well, what must x be? For 3x to equal 9, x must be 2, so 3 squared. So that gives us second order over here. And now we want to look at entries 2 and 3, where we keep this concentration constant and we change the concentration of hydroxide. So we're going to do the same thing. And again, I would just do the highest concentration on top. So 0.09 divided by 0.03 equals 0.00828 molar per second divided by 0.00276 molar per second. We're left with 3 to the x equals 3. Well, x must equal 1. And now we can put together the rate law for our reaction. So the rate equals our rate constant K times the concentration squared. That's what we found here, times the concentration of hydroxide to the first power. That's what we found here. And then the second part of this question, calculate the rate constant with proper units. Well, all we need to do there, we know the rate law now. We know the rate law. So now we just want to plug in basically one of these experiments. We're going to plug in this concentration, this rate, and we're going to solve for the rate constant K. And the same thing, you could do the same with experiment 2 or the same with experiment 3. The important thing is you need to use concentrations and rate all from the same experiment. So that's what I did down here. I just used experiment 1. So here's our rate, 0.0248 molar per second equals our rate constant times our concentration, 0.06 squared, times our other concentration, 0.03, and that's to the first power. Square that, multiply those together, I get a concentration that's cubed. And now I just need to solve for my rate constant K, so I can divide that concentration across, this molarity cancels out. 1 of these 3 cancel out, and that's going to leave us with units of rate constant. I think they asked for 2 significant figures, so that would be 230 molar to the -2 times inverse seconds, which are the units of rate constant for a second order reaction. And then the next thing I guess they could ask, so part C for this question is probably, okay, given this rate constant and 2 new concentrations that aren't up here, what is the rate for the reaction? And so again, we would just use the same rate law. You would use your new rate constant that you just found. You would use the 2 new concentrations they're giving you under new conditions, new reaction, to find what is our rate, our new rate at these different concentrations. And so hopefully that helps with question 14.34.